Good morning, good afternoon, good evening, wherever you are on this planet, and welcome to our SETI Live. Today, we are going to talk about the DART mission, a mission that was recently sent and impacted an asteroid, a mission led by NASA. And also for this mission, we are extremely honored and extremely happy to have Dr. Andy Cheng. How are you, Andy?
Great. And even better since September 26th.
I can imagine. So, but first of all, Andy is a planetary scientist. He's a planetary scientist at Johns Hopkins University, APL, and is a lead investigator for the mission. So he's really, truly the perfect person to tell us and give us some update about the mission and what happened and what will happen next. So I remind our viewers that we are going to take some questions later on. So please feel free to write them down in the chat, wherever you are using to watch us right now. And we will take the time to answer to your questions. So for those who have been living under a rock over the past 2 weeks, maybe, Andy, can you remind us what is the DART mission?
DART is the Double Asteroid Redirection Test. And it was the first planetary defense mission test of a technique to change the orbit of an asteroid. So the idea is one day we may be in the situation of having an asteroid heading for the Earth, and we may want to try to prevent the impact. Well, one way you can do that is by taking a spacecraft and smashing it into the asteroid and making it change its course. So it will miss the Earth, save the day. That's the idea anyway. So DART is a test of that. And all I could say is it was a smashing success.
That's what
happened. One of our greatest hits.
So on September 26th, the DART mission impacting Dimorphos, the moon of Didymos. And
yes.
You were watching it. I was watching it. The world was watching it. In fact, we had a live 2 hours, 1 hour and a half before the impact. Yes. So what happened?
What happened was the spacecraft, it was a good result. We hit the asteroid. But in order to do that, the spacecraft was autonomously controlled. So it had to guide itself to the asteroid. It had to find its target. And the interesting thing about it is that the target is the moon, the small moon of the asteroid Didymos. And the spacecraft is not actually able to see that moon until just about 1 hour before the impact. And we would have turned autonomous control. So the spacecraft controlling its own trajectory, controlling everything about itself, no longer under ground command. That was done 4 hours prior to the impact. At that time, the spacecraft could only see Didymos, the main body, cannot see Didymos and Dimorphos as separate bodies yet, because it's just too far away. And then some 3 hours before the impact, the moon, which is the actual target of DART, actually slips behind the primary body. And also, it cannot be seen for that reason. It's actually the Didymos is in front of it. And it's only 1 hour or a little over 1 hour before the impact that Dimorphos comes out from behind the Didymos. The spacecraft can see it. And then the spacecraft's job is, it has to recognize that it sees a new body there, and and identifies it, that is its target, and then it has to lock on. So we're, of course, watching this from the ground. Spacecraft, okay, yes, it sees the new body. Okay, yes, it's locking on. And then the precision lock happens. At that point, the spacecraft says, okay, I'm now going to change and start guiding toward the moon instead of the primary body. And so when that happens, you go, yay. That's still maybe half an hour or so before. And then as you get closer and closer, you see first all the objects get bigger and bigger and bigger in the pictures. Then we see the moon as the center of the picture, and the main body getting larger and larger, and actually finally moving out of the frame. Okay, so that's all very good. That's what happens. That means the camera is securely locked on, and the spacecraft is locked onto its target, and it gets closer, bigger and bigger and bigger and bigger and bigger. And so finally, we see the last picture. Well, at the end, the target, which is not a big body, it's only, it's half the size of the Eiffel Tower, or the size of a big football stadium or something. It's filling the field of view of the camera. So, okay, we're almost there. And then we see the last picture, which comes in. It's only a partial picture because, well, the spacecraft hit the target. It's not able to send the rest of it.
Yes.
And so that's, yeah, so we're all cheering. And yes, it's already.
That was the success for you.
That
was
was
the primary goal. We were not 100% sure that the auto-guiding system will basically be able to identify. And I mean, there is always something that can happen, software or whatever. So that was the primary.
That was the primary part of the space mission. But then, okay, now we have to use the ground-based telescopes to see that we, in fact, changed the orbit of the moon. So that was the second part. That's, in some sense, the investigation is only just starting when we have a successful impact. Then the observers actually, within minutes, the reports started coming in from observatories all around the world. Hey, we see Dimorphos is getting brighter. It's getting brighter. And then within the first 5 minutes, the telescopic images showed that there was a very fast pulse of material ejected from the moon. And then over subsequent hours and days, you saw the development of these streamers of material coming out, and then the development of a nice dust tail, just like the tails of a comet. So we activated this asteroid. It's the same kind of well, it's an active asteroid or a main belt comet, that kind of object. But it was caused by the DART impact, releasing the ejecta, which then gets pushed away from the body, away from the sun, so in the anti-sunward direction, forming a tail just like a comet dust tail.
So we created a comet.
We created an artificial comet, yes.
So before we go into the detail of this, I want to say that we have people watching us from Portugal, Central Florida, from Vicksburg, from Explore Scientific. That's a company, that's not a place. But thank you for watching us. From Kentucky, USA, California, Indonesia, Urban Hawk, upstate New York, Italy, Comolacque, Miami, Florida, Saskatoon in Canada, Stanford, California, very close to here, Venice in Italy, Glasgow in Scotland, Nigeria, and more and more places, more Italians, and from Missouri, Mexico, etc. You are watching SETI Live on the DART mission, and we have with us the lead investigator for the mission, Andy Cheng, who's telling us a bit what happened in the back scene and also what's going to happen next. So we saw the impact from the ground. In fact, the Unistellar Network also saw it with this tiny telescope here. We managed to saw the plume and so on, which is, I was absolutely amazed. Frankly, I was expecting a brightening, and in fact, I bet that it will be magnitude 2 magnitude, and people thought I was crazy, but it was 2.5 magnitude. I just got the number from Ryan, who analyzed the data with Ariel, and then we saw the plume. It was impressive. So, did you expect something like that yourself?
Yes, actually. It's pretty yes, papers back in 2015, 2016, yes. So we did expect to see something like this. I have to say I'm very gratified and surprised that we had so many observatories all around the world looking. Literally all 7 continents, there were observatories watching the DART impact. And
I saw some data coming from Antarctica.
Yes, even Antarctica.
From JWST, HST, all the space telescope facilities also observe it. But there was one telescope that observed it, one space mission I want you to talk about, the CubeSat, Licia.
Yes. So Licia is the Italian CubeSat that was contributed to DART by the Italian Space Agency. And this was the first Italian deep space mission. And what a way to start a space program. It was a fabulous success. And, so they launched as a 6U CubeSat. So it's about a 14 kilogram sort of suitcase-sized body, small suitcase-sized spacecraft. It was released 15 days before the DART impact, and then did a separate flyby to look at and return these marvelous pictures I think many of us maybe have seen. Incredible pictures of the ejecta plume, and also looking at parts of both Didymos and Dimorphos that DART could not see, because DART
Mhm.
only sees one side, the side that it comes in and hits. But LICHIA flies past and it's able to see the other sides as well. So wonderful
So Licha was a
images,
success. Yeah.
big success. Still, they've returned now the majority of the images that they took, which is also incredible. We thought they would have to wait much longer. But again, the spacecraft has performed better. And also, we've actually had better experience with how much tracking time from the Deep Space Network. The NASA Deep Space Network has been able to give us more tracking time than we originally planned. It's because of the Artemis not having launched yet. Whatever.
That's that's a good side of having a mission.
Yeah. Well, no, if Artemis had launched, they would, of course, required much more tracking time.
Of course,
LICHIA would have had less, and we would have
yeah.
had to wait longer to get the images down.
Yeah, for our viewers, we had I was at the IAC in Paris last month, and we had I had a conversation with the Licha team, engineers, as well the lead of the IAC mission on this. So you can have a look on our YouTube page. It's a recorded SETI Live that I did with them. And at the time, they truly had no idea whether or not Licha will be a success or not. So I'm very happy for them and for you as well, that we have such a beautiful pictures taken from this CubeSat. I mean, it's a new technology, and it's great it worked. Okay. All right. So can we say that the mission was a success? Can you tell us the requirement that you had from NASA about this mission?
Okay. So the requirement, the most important one, of course, is to hit the moon with the spacecraft at this opportunity, the October 2022 close approach of the Didymos system to Earth. So use during that opportunity to hit the moon with the spacecraft. And then we had a requirement to change the orbit period of the moon. Of course, we're confident that if we hit the moon, the orbit period change will happen. I mean, that's just physics, okay? So that's not a problem. We had a requirement for how much we had to change it. We actually changed the orbit period by 32 minutes approximately. So it went from 12-hour 55-minute orbit to a 12-hour 23-minute orbit. It's a big change. So the reports were coming in after literally only a few days. Yeah, it looks like the period's changed. Looks like the period's changed. And after just, I think, a couple of weeks, we already had a good enough, solid set enough measurements to have a good measurement of the period change. So measure the period change. And the last is to determine the amount of momentum transfer and study the other dynamical effects of the impact, but primarily to determine the amount of momentum that's actually transferred. And the question is that the momentum that you put into the body to change its motion is actually greater than the amount of momentum that the spacecraft carries into the impact. And the reason for that is that the impact causes ejection of material. This is the plume material. It's ejected back in the direction the spacecraft came. And so the impact site, or the crater that's formed, it's acting like a little rocket motor. It's throwing material back at you. And so that gives you a little extra push. Or in our case, it turns out to be a big extra push. The extra momentum that was transferred because of the ejecta was more than what the spacecraft brought in. So that's something very important, of course, for any future deflection attempts. If we're trying to deflect an asteroid, we should know that it's very likely that we'll actually push the asteroid with an impulse that's, considerably greater, 2, 3, 4 times greater than what the spacecraft actually brings in.
That's an interesting point. Yeah.
Yes.
Because in space in physics, of course, there is no friction. So the ejection of material is basically pushing away the moon. How was the impact with respect to the orbit of the moon? Was it on the side? Was it in exactly aligned?
Okay, all right, the orbital motion of the moon. I don't know if I can do this. The moon's coming around here. The spacecraft is almost head-on impact.
Okay.
And so what that does is it reduces the instantaneously reduces the orbital speed. So you have less centrifugal support. And that means that the moon falls closer to the primary. When it falls in closer, it speeds up. This is to conserve angular momentum. It's just like when your skater is twirling and you pull on your arms, you twirl around faster. So when you come in closer, you swing by faster, and then you go past, the orbit becomes eccentric, and so you go out farther away and you slow down again. Turns out that the slowing down is more than the speeding up. So overall, no, I said it backwards. You fall in closer, you speed up. The speeding up is more than the slowing down, and so overall the orbit period reduces. So
okay.
So this is how it's a little bit confusing because we hit the object head on in its motion, so instantaneously it slows down. But then because it falls in closer to the primary, overall the orbit period is reduced and the orbit speed is actually increased.
Okay. All right. I see that we have questions already coming and people joining us from Oregon, Germany, East Tennessee, Geneva, and Prague. Dobry den. And San Bernardino, California, Illinois, Italy, Scotland, more Scottish people, 3, 4, 5 Scottish people, a lot of them. Hello. We are watching a SETI live on the DART mission. And the fact we have so many people joining us from so many different parts of the world clearly shows that there is a strong interest for this mission. Because the goal of this mission is truly to defend the planet, right? To learn how we can defend the planet. If one day we find an asteroid that could impact our planet, we will need to deflect it. And this technology the DART mission is basically a test to test this technology and to learn about asteroids. So what did we learn about the asteroid itself?
We're still working on that, but yes, what we hope to learn is, we are seeing that the period change was at sort of the middle to upper range of the predictions that were made as to how much this momentum transfer could be. So there's more ejecta than, there was faster ejecta as well. And we have to try to understand how that could come about. So that has implications for what kind of material, how strong is it, how porous is it, and things like that. We also learned from the images, and many of you have seen probably, that the size and shape of both Didymos and Dimorphos was also a little different from what was predicted. So it turns out that the Didymos in particular is actually smaller than was inferred from the radar data. This is not surprising because of the geometry of the 2003 apparition, where the shape models were originally derived by radar. It turns out that the viewing site was almost equatorial, and that's why the polar dimension of the body was uncertain. And it turns out that Didymos is smaller than we had, considerably smaller than we had expected. Also, the shape of Dimorphos is different from what was predicted. And so there's a lot of things like that we're going to have to all put together to understand why we saw the amount of ejecta that we did, and also why the period change was what it was.
So those will be published in the future. There's probably
that's all good. Yes, that's what we're all working on. Right?
Yeah, we're also working on it, just so you know. The Interstellar team we're working on the paper. So from our observations, we're gonna try to get some good information about the asteroid impact itself, and see if we can kind of derive the amount of energy and so on. So those are a lot of scientists in the world are working on this at the moment, using their own data or the data coming from the spacecraft, if you have access to them. That's good. We have a lot of questions, a lot of people joining us, but before that, so the mission DART mission is over now. Now we have the analysis of the data and so on. But there is a new mission that is in process, right?
Yes.
Called the ERA mission. So can you tell us a bit more about this mission?
ERA is the European Space Agency mission. It will rendezvous It's a mission to go back to the same target, Didymos, the Didymos system, and study the outcomes of the DART impact. So we have high hopes for them that they will be able to find, for instance, the crater that DART made, measure how big it was, because that's something we don't know, measure its shape, and also make very detailed studies of the orbital motion of the moon. We're only measuring a period change. Of course, we've changed everything about the orbit. So I'd like to measure the other ways that we have changed the orbit. And likewise, when you change the orbit, you also need to change the rotation state of the moon. We don't know what the rotation state of the moon is very accurately, but Hera will measure that now. So there's lots of interesting dynamics questions. Much more we'll learn about the materials that the moon's made of, and also its interior structure, its moments of inertia, it's whatever, lots. So Hera is a very exciting mission. Hera and DART were tied together at birth, even from the beginning. And so we're very excited now that after DART, we will have Hera mission. The Hera mission is actually now in development. They're in their critical design review. So the spacecraft is being built. It will launch in 2024, arrive at Didymos at the end of calendar year 2026. So very much looking forward to that.
All right. That's going to be interesting, definitely, to see the impact of the crater impact. And probably see some changes on the surface of the moons and on the surface.
Oh, undoubtedly, yes. Yes.
Because something we briefly mentioned, there was a brightening, right, of 2.5 magnitude. But right now we're taking data with our network, and we see that it's still, Didymos system is still brighter than expected.
Yeah, I think it's actually still a little brighter than it was before.
Yeah. So that means that there is a swarm of fragments or something, clouds of material around it.
Yes.
All right. It's a very, I mean, I'm impressed still when I think about it, that we basically launched a spacecraft that disrupted a binary system.
Yes, we have actually rearranged the solar system for the first time.
Yeah. All right. I want to mention that in 2007, we had a program at UC Santa Cruz with students to build an innovative concept to explore an asteroid. And the student I chose Didymos at the time and Dimorphos, the moon. And Julie Bellarose was a part of this team. And Julie is now one of the JPL engineer who has been kind of in charge of the development of the software to control the spacecraft and to impact the spacecraft. So I have my small involvement in this project somehow through this program.
And Julie Bellarose is the navigation lead for DART also.
Exactly. So kudos. Okay, so let's go through some questions here. We have a question from Lionel. Did the impact only change the orbit of the moon, or was the entire system affected?
Yes, the entire system is also affected. That is absolutely correct. It's because the orbits the two bodies are gravitationally bound to one another. And so that when we change the motion of the moon uses its own gravity to tug along the primary. So it brings the primary along with it. And so, yes, the orbit of the moon changes relative to the moon, the orbit around the primary changes, but also both bodies, the orbit around the sun is changed by just a little bit, because the Didymos is so much larger that the change in the orbit around the sun is very small, and it's in fact hard to measure. But yes, it is changed.
Is it changed? And we will be able to know this when we observe continuously Didymos, or when we send Hera, because Hera will basically give us the new orbit with very accurate.
I think it's possible that Hera will be able to measure it. It's also, there's some efforts also going on right now to try to measure it, to see whether, for instance, if we can do occultations with it or something like that you can measure. There are going to be people trying to measure.
That was my announcement. In fact, the SETI Institute is involved with the ACROS team, and we are going to use our unistellar network to try to observe by occultation Didymos and be able to measure this position in space, so hopefully
Yeah.
detect a potential deflection. So that's
Okay, good.
so we're working on that too.
Yes, good.
Okay. What about the double tails? That's a question from Stephen Collins.
Could you repeat
Maybe
that? I didn't understand.
the double tail. There was some the impact
Yeah.
showed there is multiple tails and so on. There is these distant tails, 40,000 kilometer length right now, long, sorry, and then there is small tails. So what are those?
A good question. The team is currently arguing about that, and I don't know that we have any good ideas yet either. I don't believe solar wind pressure is very important, but certainly it is solar radiation pressure that's responsible for controlling the motion of these, primarily responsible for controlling the motion of the dust particles down the tail. So why it's split is, I think we're looking for, we don't have any, we're working on that, and I'm not aware that we have a good explanation for that at this point.
All right. And yeah, so you have these tails been observed by Hubble Space Telescope, by
Yes.
JWST as well. So we are going to have multiple wavelength observations from the ground. So
Uh-huh.
probably they're gonna tell us a bit about the size of the particles, the composition.
Absolutely,
maybe.
yes. Well, there's people doing that. Obviously, there's many people doing that kind of modeling, and yeah, it looks, yeah. So how do you get a double tail? Well, you can have multiple release events. You can, I don't know. Just it's
still a
just odd.
mystery.
We don't have a good idea.
Okay. Dave Merritt asked us about the type of calculation that was needed to hit the target. What exactly was the algorithm behind it?
Okay, the main idea. The nature of the algorithm, it's proportional navigation is what it's called. It's also what's used in a lot of guided missiles to go ahead and hit maneuvering aircraft targets or missile targets or whatever. And the basic idea is that if you're headed for a target, the direction of your line of sight to the target is not changing. But if you're going to miss, the direction of your line of sight changes as you track the target. So what the proportional navigation does is it tries to null out the rate of change of your line of sight. And if you do that, you can show that you will always hit your target. So that's the basic idea. It's used, as I said, in guided missiles, the ones that are meant to go after and home in on and shoot down something.
Okay, and so this technology can be used on different type of asteroid. Like we have 100-meter size asteroid here.
Yes.
Do you know what's the smallest size we could use? That's something, a question related to the one from Laurie Wright.
The smallest size you can hit. Well, there have been missile tests, guided missile tests, maneuvering targets, which hit things an awful lot smaller, right? Your airplanes, or even the missiles that you shoot at are all, so they can be very small. So yes, there's this method can be used to hit things that are really, really tiny, much tinier, in fact, than you would ever need to for the asteroid impact hazard. Because, if you have an asteroid out there that is 10 meters or 20 meters, and even if it does hit the Earth, chances are it will not get through Earth's atmosphere. It'll blow up high in the, so it may not cause much damage on the ground. You may not need to intercept something that small.
Okay, another question from Stephen Collins. Has the color of the system changed?
Okay. I probably, there were observations. A number of people made observations of that thing. I don't know that I should actually announce their results, however. So
I can say something about us.
Okay, go ahead. Let you say.
At Unistellar, we did show it live, and during the recording, we noticed that a change of color. Just after the puff appeared, you could see clearly there was a change of color on live. So we are working on that.
Good. Yes.
So, but why the change of color? Well, it's probably because either there is material excavated from the inside, right? But is that possible as well that the change of color could be due to the destruction of the spacecraft and the amount of material inside and so on?
Well, the amount of material that are in the ejecta is, of course, much greater. It's thousands or even much greater than the amount of material in the spacecraft. So I'm skeptical that you'd actually see any effect from spacecraft material. But I think it's one of the comments briefly showed up. It's yes, space weathering is what we're talking about. Is the material at the very surface of the asteroid that's exposed to space radiation, particle radiation, and meteoroid impacts and so on. That kind of material has its colors altered, its albedo changed, and that sort of thing. So that's what we call space weathering. And the material down to some shallow depth is going to be space weathered. You lift that up and it will look different from what material that's fresher, that's deeper down. Not
we have a lot of questions, but we're not going to be able to answer to all of you because I told you we're going to take 30 minutes only of your time, Andy. I know you're extremely busy right now. I have two more questions, one about you. So how did it feel over the past 2 weeks? How did you feel yourself about the past 2 weeks? What is the moment that you think you can share with us about this entire mission?
Oh, it's been like a dream. It's been crazy. As I said, I think coming on, it's been crazy happy, as you can imagine, and many things going on. And also being very impressed by the amount of work that people have been doing, just observing this and looking to see, oh, look what happened, and understanding. So the analysis, both the analysis and the continued observing effort is just really amazing to me. So yeah, it's been like a dream.
You have not
much better than the week before the impact.
If you have to compare this in terms of life, what would be the same level?
Oh gosh, I was primarily anxious, tense, worried.
Well, congratulations. I'm happy to see you smiling and happy because frankly, I'm happy as well that it did work. And a lot of people on this planet are. So congratulations to you and to the team, because I know there's a huge team behind it. And
it's been great.
We learned a lot.
An honor, actually.
Yeah. So that was the SETI Live with the SETI Institute and Andy Cheng. Andy, thank you again for your time. I want to make sure that if you have more questions, you can write them down into our comments on YouTube, on Facebook. We take the time to answer to some of them. This is not the last SETI Live we have on the DART mission. Just people, it just happened. There will be more results, more science, more fantastic mysteries that have been revealed with this mission. So Andy, are you coming back if I invite you again?
Sure.
Okay.
Okay.
Thank you very much. I'll let you work. And thanks everybody, all our viewers watching us on all those platforms. We have the SETI Institute, a non-profit organization. We do scientific investigation, searching for life on other planets and in the universe, but we also study asteroids, as you may have noticed from what I said today. If you feel inclined, you can make a donation at seti.org/give now. You can also simply follow us, register to receive our newsletter, follow us on social media, participate to the conversation, like this video, people, come on, like it, so it pop up magically on the feed of other people. Send us comments, questions, and and enjoy the dark sky. Watch up, look at the planets and the stars. Look at Jupiter tonight. It's beautiful if it's clear. Okay, and thanks again, Andy. I hope to see you soon in a conference somewhere. I'm coming to Baltimore in December, so I may stop by to say hi to you if you're around.
Okay, very good. I look forward to it.
Bye-bye.
Bye-bye.